So these are the first part of Unit 4 notes. We're going to cover nuclear chemistry. We'll start with a couple definitions. Radioactive decay is the decomposition of a nucleus to form a different nucleus. I'm going to move kind of fast, which means you'll probably have to pause if you're taking notes for yourself. Something else we'll be spending more time on in the next lesson is half-life, but we'll go ahead and define it here as part of these notes. Half-life is the amount of time it takes for a sample to decay by half. So everything has a half-life. You can also think of this as like a shelf life. So if I had 100 grams of something, the amount of time it takes for it to get to 50 grams would be considered the half-life. There are 3 types of decay we need to define. The first being alpha decay. Sometimes alpha decay is represented with the Greek letter for alpha, which is this funny looking symbol here. In alpha decay, the nucleus releases an alpha particle, represented by this symbol. It's just a helium atom. So anytime we see the term alpha particle or alpha decay, this is what we should be plugging in. Of the 3 types we're going to talk about, alpha decay is the least energetic, meaning it can be stopped by something as thin as a piece of paper or by your skin. And if we're doing an example of a nuclear reaction that undergoes alpha decay, if I have this atom and it undergoes alpha decay, I would say I'd represent that with an arrow. And on the right side of the arrow, it's releasing an alpha particle, which we said is representative by this helium atom. And so from here, if I think of this arrow like an equal sign, I just need to make the numbers on the top match. So if I'm trying to determine what this should be, then I'm going to add these 2 numbers together so that they equal 245. And then same for the bottom. I'm going to add these 2 numbers together so that they equal 93. And then this number on the bottom is how I can determine what this symbol is. That's your atomic number, which corresponds to the element number on the periodic table. So element 91 is element Pa. So if one of these things was missing from this equation, that's how you would find what the missing piece was. The second type of decay we're going to talk about is beta decay, represented by the Greek symbol beta, which is like a squirrely bee with a tail. In beta decay, the nucleus releases an electron, shown by the symbol 0/-1e. This one is kind of in the middle of the energies, meaning it can penetrate your skin, but if you have like metal or a thick piece of plastic, that can stop beta decay radiation. And here's an example of that. I have an atom of iron undergoing beta decay. I'd represent that with an arrow, producing a beta particle, this symbol here. And then I just make my math match if I'm trying to figure out what goes in this blank. So 0 plus 50 has to add up to equal the other side. -1 plus 27 has to add up to 26. And then that number on the bottom, I can use to determine that that's CO. The third type of radiation is gamma decay. And the Greek symbol for gamma is kind of that like weird looking Y. In gamma radiation, the nucleus just releases pure energy in the form of gamma rays, represented by this symbol, 0/0 with the gamma symbol. This one's the most energetic, meaning you need some really thick concrete or lead to stop the penetration of this particular radiation. And an example of that would be if I had an atom of nickel undergoing gamma radiation, I use my gamma symbol and my math adds up. So this atom looks the same as this one, but I put that little star there on the left side of the arrow to show that this guy was super high in energy. It released some of that energy, and now the atom doesn't have as much energy because I've removed that asterisk. Next, we're going to talk about some nuclear reactions. There's 2 types of nuclear reactions we have to cover. The first being fission. Fission reaction is the splitting of a large atom into two or more smaller ones. This is not a common process in nature. It does not occur on its own naturally. This is something that scientists manipulate atoms to cause to happen. It's a very energetic reaction, and then we can harness that energy for practical uses. One of the uses is the atomic bomb. Another one of the uses is the generation of electricity in nuclear power plants. And so an example of something undergoing a fission reaction, we have this atom of uranium. It breaks apart into two smaller atoms. As long as I gave you two of these things, you should be able to fill in the other blank. Because again, if this is like an equal sign, the numbers on the top have to add up to equal each other on either side of that arrow. Same for the numbers on the bottom. And then of course the number on the bottom can help you predict what element it is. The second type is essentially the opposite of fission. This is called fusion. This is where two smaller atoms combine to make a bigger one. So we take two smaller atoms, we ram them into each other. There's a lot of energy produced in that process, and then we end up with something larger. This is something that occurs naturally. This is what happens in stars or in the sun. If we could harness the energy of this, this is how we would produce a hydrogen bomb, and very, very energetic process. And an example of that is if I have two smaller atoms and I cram them together, I can produce something bigger or something heavier. And again, same story. The numbers on the top have to add to equal each other. Numbers on the bottom have to add to equal each other. And then I would use that atomic number on the bottom to predict from the periodic table what elemental symbol. A few other important particles and their symbols that might be useful when balancing nuclear equations, which that's what this is. This is a nuclear equation, and we balance it to make sure that the numbers add up on either side. If you have to represent a neutron, we would do 1 over 0 n. If we had to represent something called a proton or a positron, 0 over 1 p. And again, an electron is 0 over -1 with an e. So let's do a few examples. This document is in Canvas. You do not have to turn this in for a grade. It is a practice page, and the key is also posted in Canvas so that once you complete some of these practice questions, you can check yourself in the key. And then there is a checkpoint assignment that is a grade, so make sure you complete that. Okay, so if we have alpha particle emission, that's talking about this thing, this helium atom. And the word emission means that we're going to put something on the right side of the arrow because it is being released. And so if it's an alpha particle, it's this guy. If it's being emitted, it's on the right side of the arrow. So we fill in that. And now we got to figure out what goes in the blank. So 4 plus some number has to add up to 210. 4 plus 206 equals 210. And I do the same thing with the bottom. 2 plus what equals 84. So 82. And then I check the periodic table and I find that element 82 is Pb. That is alpha particle emission. Then we could also be talking about beta decay. So a beta particle from our notes is represented by that guy. If it's decaying, that means it's being emitted, so that thing is going to go on the right side of the arrow. So I fill in a beta particle here, and then I might do my math. 0 plus 14 equals 14. -1 plus 7 equals 6. And element 7 is nitrogen. Electron capture. We didn't do an example of this, but we're going to use some contextual clues. So I said the symbol for an electron, 0 over -1, E. When we talk about capture, that means it's going to be on the left side of the arrow. because whatever this atom is, it captures that electron. It combines with an electron to make something new. So we're going to put that electron on the left, and then we'll do our math. Since the arrow's over here now, we're going to do 106 plus 0 equals 106, and then 47 plus -1 equals 46, and then we use that number, that atomic number, to find that 46 is PD. We could also do something called positron emission. So again, a positron was 0 over 1p. That was one of the last things we defined. Emission means it's being released, or it's on the right of the arrow. So we put a positron on the right, and then we add our numbers up. 0 plus 116 equals 116. 1 plus 49 equals 50. And then element 49 is indium, IN.